Hello everyone and welcome to our learning part on power quality. We will explore why power quality is vital in the semiconductor industry. My name is Sarah Esarabadi and I'm the Vertical Marketing Manager responsible for the semiconductor industry. In the semiconductor industry, where the precision and quality of the end product are quite important, power quality is a critical element in the production. Poor power quality can lead to significant operational disruptions and financial losses. Now let's take a closer look at what could happen if power quality falls short of standards in the highly sensitive environment of semiconductor manufacturing. Picture this. Our plant operates plenty of individual production machines, each one fine-tuned for optimal performance. At the heart of it all lies our sophisticated IT infrastructure, orchestrating every move to precision. Imagine then a voltage dip just 150 milliseconds. Such a brief disturbance has the power to create problems across the production floor, where even the most robust machine might malfunction. The disruption extends to our IT systems, leading interruptions in our network, pausing the production. Furthermore, sudden power loss can cause an incorrect shutdown of the manufacturing equipment, potentially scratching or breaking wafers. Electromechanical deposition processes can be disturbed, causing inconsistent or incorrect material layering. Moreover, abrupt changes in heating and cooling can introduce thermal stress, leading to microcracks in the wafers. As well as voltage instabilities can disrupt photolithographic processes, leading to incorrect patterns, transfers and detects. And finally, incomplete or unregulated etching processes can leave behind residues or cause over-etching, both of which can affect device performance. All these consequences lead to high financial setbacks. This scenario highlights the critical need to maintain strict power quality standards, emphasizing the substantial impact on operation efficiency and financial health in modern semiconductor manufacturing. In Malaysia, a study was done to estimate costs associated with poor quality, namely voltage sags. Meters were installed at appropriate locations in the power grid. In the table, you can see the cost per event for different industries, with semiconductor having the highest cost per event of $720,000, followed by the metal, aluminium and copper productions with $160,000. Semiconductor facilities rely on a high level of power availability and quality due to the sensitivity of specialized manufacturing equipment and precision of process controls in the wafer fabrication. Voltage sags or voltage dips, the most common types of power quality issues experienced in the semiconductor industry, cause loads to de-energize. This leads to production interruptions, scrap of raw materials and potentially millions of dollars in loss within the unprepared fabrication facility. The specification for semiconductor processing equipment, SEMI F47, voltage sag immunity standard provides a target for the facility and power utility systems and defines the threshold that a semiconductor tool must operate without interruption. Due to the sensitivity of equipment and process controls, recognizing semiconductor factories require high levels of power quality. The SEMI F47 specification defines the minimum voltage sag immunity that is needed for semiconductor processing and test equipment. So, as we look at this slide, we see the essential benefits of maintaining high power quality. Protecting equipment from damage, we avoid costly repairs and interruptions. This directly enhances the product quality, ensuring our semiconductors are correctly produced. With a stable power, our production runs efficiently without interruption, which boosts productivity. And it's not just about productivity, it's about cost savings, less downtime, means better financials. Lastly, a stable power system is critical for the integrity of our data, guaranteeing the precision of our monitoring and control system. As we have seen, power quality is crucial, particularly in the semiconductor manufacturing. Now let's take a glimpse at what we will cover in this learning part. We will dive into the essentials that are key to understand power quality. We want to give you some insights about the motivation behind the power quality monitoring and its fundamentals. We will also take a look at the standardization framework as well as the measurement and evaluation methods used in the world of power quality. I'm very pleased to now introduce you our expert, the Product Lifecycle Manager of our Power Quality portfolio, Dr. Michael Schwenke. Michael, the stage is yours.
So welcome to my presentation, Power Quality and Monitoring today. And I will give you some information about Power Quality essentials and our Power Quality instrument portfolio today. Let's have a look at the agenda today. At first, I would like to tell you something about the motivation for power quality monitoring, then about power quality basics, the standardization framework, power quality measurement methods and evaluation, the Siemens power quality portfolio, hardware and software, and some application examples. Let us begin with the motivation for power quality monitoring. At first, what is power quality? Power quality is the summary of voltage quality. In an ideal case, the voltage waveform is pure sine wave. Nonlinear loads can disturb the voltage waveform by these disturbances, but these disturbances are limited by standards. The second part is the availability, 24 hours per day, 7 days per week, no voltage events. And the third part is the service quality. Is a continuous power quality monitoring installed, and are both sides, supply side and demand side, observing the compliance with limits? The main motivation for power quality monitoring is if you cannot measure it, you cannot improve it. The power system is changing rapidly. To adjust to ever-present changes in the system, the continuous measurement should be preferred over spot measurements just in case of problems. What are the impacts of bad power quality on consumers, manufacturers, and utilities? Always financial losses due to interruption of processes, production loss, waste of raw material, equipment damage or aging, loss of data, or increased losses in electrical equipment and distribution systems. Let's have a look on power quality phenomena and events. Type 1 are continuous phenomena like frequency variations, voltage or current unbalance, flicker, voltage or current harmonics and interharmonics, and supraharmonics in the frequency range from 2 kHz to 150 kHz. Type 2 of power quality disturbances are voltage events, such as voltage supply dips and interruptions, supply voltage swells, transient overvoltages, or rapid voltage changes. And there's another type which is inserted in the power system, so-called mains communication systems. These are control signals which are inserted to control equipment in the power system by voltage pulse patterns. I give you a short explanation with the picture on the right side. You see here that the waveform isn't a sine wave. There are some disturbances visible caused by low voltage phenomena like harmonics, which disturb the sine waveform, and there are additional spikes on the curves you see here, which are caused by very high switching frequencies and are measured as so-called supraharmonics. The origins of power quality problems. Who is responsible for power quality disturbances? We have the supply side, which is responsible for frequency variations, voltage variations, and voltage interharmonics and harmonics, and voltage unbalance. The demand side is mainly responsible for current harmonics and interharmonics, current unbalance, reactive power, neutral currents, and rapid voltage changes. Both sides are responsible for power quality problems like supply voltage dip swells or interruptions, flicker, and voltage transients. So supply side and supply and demand side are responsible for good power quality. At this time, I would like to give you an application example. It's a frequency event in Europe, which happens in January 2021. The continental European grid frequency dropped below 49.75 Hertz. I recorded the 10-second frequencies and the 10-cycle minimum frequencies in this observation period with a Q200 device in Berlin in Germany. The frequency was stable before the problem occurred. The frequency was around 50.02 and 50.03 Hertz. And then a frequency drop happens within 13 seconds. And the frequency went down to by 270 millihertz. Such frequency drops are very, very seldom. And the problem is who was responsible for this event here. Let's go to the next slide. A closer inspection was done by the European utilities, and this event was measured in different countries, starting from Eastern Europe to Dresden, Berlin, Vienna, France, and so on. And it was identified from the slope of the frequency plot that the problems happened in southeast of Europe. According to the report, see the link on the slide, there was an overload of a busbar coupling in a substation in Croatia. A protection trip at 2 p.m. 4 minutes and 26 seconds disconnected the two connected bus bars, and the problem started to and the power grid came back to the level of 50 Hertz. Here you see in orange which part of Europe was disconnected from the blue part of Europe. So let's go on with the power quality standardization framework. You see that the power quality standardization framework consists of 4 blocks. The block 1 are the measurement methods. The leading standard is IEC 61000-4-30, where the measurement methods are defined. We are working on edition 4 at the moment. Edition 3 from 2015 is still valid. The standards who are referenced there are the 4-7 for harmonics and interharmonics and 4-15 for flicker measurement. Block 2 shows the product standard for the so-called power quality instruments, PQIs. There are 2 different classes of the PQIs defined, class A and class S. And for each class, the functional and uncertainty requirements are described in these 2 product standards. Part 1 is the product standard itself, and part 2 are the functional tests which have to be passed by power quality instruments, class R or class A. There's also a technical report about cybersecurity requirements for PQIs available. It's a solution until Cyber Resilience Act for products with digital connections is available. It's expected for 2026. Block 3 contains all the power quality evaluation and management standards, technical reports, and the most important standard for us is the EN 50160 from 2020, which describes the low voltage characteristics of electricity supplied by public electricity networks. There's also an IEC standard available meanwhile with edition 2, assessment for power quality. It's a little bit different from EN 50160, and one is developed in Senelec and another one is developed by IEC. I don't see a fast standard together between Senelec and IEC. It's not planned to have this standard in a short future. There are also some other standards which are dealing with power quality evaluation, especially inside industrial installations, demand-side power quality guideline for operators in industrial installations, and compatibility levels in industrial plants for low-frequency conducted disturbances. And the fourth block in the standardization framework are the communication standards and data formats and data exchange formats. There we have IEC 61850-90-17. It's a technical report which describes using IEC 61850 to transmit power quality data, and IEEE 1159.3, which is meanwhile also an IEC standard, and IEEE C 37.111. It's also an IEC standard, described usually the most important data formats like PQDIF, Power Quality Data Interchange format, and COMTRADE for fault records known from the protection already. So then we can move over to power quality instruments. The power quality instruments are measuring continuous power quality parameters according to product standard 62586-1, edition 2 meanwhile. You see a list of measurement functions. This table shows mandatory and optional measurement functions and records, including aggregation intervals in Class A and Class S devices. The mandatory functions are minimum requirements. Some optional functions like current measurement are mandatory in next edition of the product standard, but there is a transition time because they were defined in edition 3, and in edition 4 we expect them mandatory. Supply voltage dips and power quality events. For these phenomena, the logging of different event types is required. Supply voltage dips and interruptions, logging of residual voltage, UMS half or depths, and the time stamps for duration. See figure 1 later, as we are already on this slide here. Supply voltage swells, we have to log the maximum of swells magnitude and timestamps for the duration. Transient voltages, the measurement of transient voltages can be useful but is not mandatory. And rapid voltage changes, start time, duration, delta U max and delta U steady state are the parameters. You see two pictures on the right side. The first is a voltage event. If the voltage goes out of the plus minus 10% voltage band, then the event starts. And if the voltage is coming back after a while to the 90% border plus 2% hysteresis, then the voltage event ends, and the event is characterized by the start time, by the lowest voltage during the event, and by the end time, so by the lowest voltage or residual voltage or voltage depth and the duration. And it's similar for the rapid voltage changes, but rapid voltage changes do not cross the plus minus 10 voltage band. They always stay in the plus minus 10 voltage band. They are mostly caused by switching of big loads. So the voltage is going down by 3 or 5 or 7%, but not by 10%. And the voltage is coming back slowly and is stabilizing on an old declared voltage or on a new voltage level, which is characterized by the delta U steady state then. It's a quite new definition, and it's only observed and logged, but not evaluated clearly in the evaluation standards. There is a clear one-to-one relation between the product standard itself and the related testing standard, part 2. For each power quality measurement function, test procedures are defined. After manufacturer's internal function tests are passed, an external certification by a lab is usual and meanwhile required by customers. So we see here, if you pass all the tests, you can get a certificate from an external lab here from Netherlands, from NMI, and that's what the customer often like to see meanwhile. Let's switch over to our power quality class A portfolio. There are 2 devices in our portfolio, which are the Q100 and Q200. I will explain the differences later. At first, what is the goal to measure power quality? Of course, the first step is the transparency in the power system. Increase power quality. It increases the power quality and avoids unnecessary non-conformal costs. Our Zipotec power quality devices measure, record, and analyze power quality long-term measurements and events. And the analysis makes the interferences in our processes visible and understandable. Interferences can be reduced with countermeasures. Stay in the loop. Here we have our 2 devices. SICAM Q100 offers acquisition, visualization, and analysis of electrical measurements according IEC 61000-4-30 Class A. It has a measurement accuracy class .2s for current and power measurement. It offers harmonic direction and harmonic phase angles in addition to the standard, and also additional function like voltage event detection indication. The Q100 is suitable for compliance measurements for use in courts. It's a good basic class A measurement, but we offer some more in Q200. Q200 has the same functions as Q100, plus supraharmonics measurement and fast transient recording. Supraharmonics are measured in the frequency ranges 2 to 9 kHz in 200 Hz bands and 9 to 150 kHz in 2 kHz bands, according edition 3 of the measurement standard. And they are recorded as 10-minute values. A very interesting function is the fast transient recording up to 1 microsecond time resolution and up to a magnitude of 6 kilovolts. The measurement accuracy for current and power management of Q200 is .1s. It's preferred for measurements in sensible production areas if there are some influence on robots or other sensitive equipment, or in data centers if it's necessary to look for electrostatic discharges and other EMC phenomena in the higher frequency range. CCAM Q100 and CCAM Q200 are external certified according to 4-30 edition 3 and IEC 62586-2 and certified externally by NMI in Netherlands. You see here the list of functions on the right side which was tested and passed the test. Another important topic for devices which collect and transmit this kind of sensible data is the cybersecurity. We installed in both devices a role-based access control. That means role-based access, of course, ensures that the user may exercise only those rights which correspond to their assigned role. So you can scale the access to the device from reading values only up to update firmware or delete buffers and so on. The central user management via radio server is supported. At second, we offer a Siemens firmware signature, and it gives a protection against firmware manipulation. Only firmware signed by Siemens is permitted to be uploaded in the device. We use the secure and reliable HTTPS protocol, and it guarantees the secure transmission of sensitive data. And all security relevant functions are stored in a security log. It's a non-volatile storage of syslog events, and this buffer is protected against power failures too, so it's always available and nobody can delete it. So next I would like to go over to a basic power quality evaluation. I will show you a PQ report evaluation via browser, including a voltage dip classification. The devices provide a power quality report in the device itself. You can select an observation period, and then all the all power quality phenomena are checked. And you see here in table 1 that all the continuous phenomena passed the evaluation. But in the second table, we see that there were voltage events. And so we offer the magnitude duration table for evaluation of the event in the report 2. The event is shorter than 200 milliseconds and the residual voltage is 73% of the nominal voltage. That's important. It's important to know that there is a so-called ITIC curve, which provides a fast visual inspection if the event itself was critical or not. Is it critical? No, because it's inside the red area in the ITIC curve, because the event was short and the voltage dip was not so high. I would like to tell you something about the system integration and data transfer of our devices. We have open and transparent protocols, and so we are able to support different software solutions. Our internal software solutions, PQ Advisor Compact and PQS and PQ Analyzer, they are using the IEC 61850 protocol to transmit operational values or long-term power quality measurements via IEC 61850 in PQDIF or COMTRADE file format. Also CSV is supported, but for connection to other systems. On the other hand, we have the CSV file export via FTPS meanwhile, so that we can connect to other SCADA systems. If the customer don't like to use our software, he can import the long-term power quality reports as CSV files from the device and extract them and analyze himself. We have also other protocols which are mainly used in energy management area, and it's Modbus TCP, and also the energy management from our EP department, Centron Power Manager, and the Desigo CC from Building Technology will support power quality evaluations in next versions, also via IEC 61850 data transmission. Yes, okay. Then let's go to the last block of my presentation. I would give you an application example. There was a question last summer, are there voltage dips observed in Germany? And so different measurement locations were invited to analyze their events in the grid. And I took part in this evaluation, and I checked my devices in Berlin. There are a lot of devices installed in the observation period from 1st of January 22 to 30th of June 22. And what happens within that time? There's an overview here, the location, Siemens AG in Germany, Berlin, Germany, observation period. I also mentioned it. And the summary is 13 voltage dips occurred, no voltage swells, and no voltage interruptions. So let's have a deeper look at two events now. Event 1 occurred on 1st of March 22. The residual voltage is 78%. It's not so critical. It was quite short, only 70 milliseconds, and only phase A went down to 171 volts. Other phases were not so heavy affected here. It's a little bit different in the application example 2, because you see the RMS curve here. This event occurred on 23rd of April in 2022, and the residual voltage in all three phases is only 30%. That means for 130 milliseconds, phase A, phase B, and phase C voltages were only 72 volts. And if we go back to the ITIC curve with the evaluation result, you see that it's outside the ITIC curve. And that could be a problem for some equipment in this low voltage installation, because it can lead to interruption of some devices or data communications and so on. I don't have the details, but it's a quite heavy power quality event here. Okay, that's what I prepared for the webinar today. Thank you for your attention.